We now start module 2 of the first chapter, systems of linear equations. So far we have talked about the basic definitions, examples and elementary row operations and elementary matrices. Now we introduce the concept of an echelon form of a matrix, and we talk about the Gaussian elimination. We illustrate these concepts with the help of quite a few examples, and I hope that you will get an idea that Gaussian elimination is a very precise algorithm for solving a system of linear equations. We begin the module 2 with echelon form of a matrix. Let us now introduce the concept of echelon form of a matrix. To be precise, row reduced echelon form. The meaning of the word echelon is wedge shaped. So, what we aim to do is to reduce the matrix to a particular form which is definitely simpler. You will understand what I mean by simpler when I formally define the echelon form, and that form is to be achieved by successive elementary row operations on the matrix. Now, this is the reason why we call it row reduced echelon form. Now, what is precisely the echelon form of a matrix? So, a matrix is said to be in row reduced echelon form if the following conditions hold. 1. Any row containing at least one non-zero entry precedes any row with all the entries 0. That means, if a matrix has a row which is non-zero, that means there is at least one entry in that row which is a non-zero entry, then that should be placed above a 0 row. So, the first requirement to achieve a row reduced echelon form would be to push all the 0 rows at the bottom. You know, the first elementary row operation, which is interchanging rows, that surely allows us to interchange, and by that if we notice any 0 row, then we can immediately push it down to bring the non-zero rows upper in the order. The next requirement, the first non-zero entry in each row is the only non-zero entry in the column that contains the 0 entry. What does that mean? So, if you look at a row, then start looking at it from the left, move along the row. The first non-zero entry which you see in the row, assuming that the row is a non-zero row, then you spot that entry and then look at that particular column where that entry is placed, then all other entries in that particular column would be 0 other than this particular non-zero entry. And that should happen for each non-zero row. The third requirement is that the first non-zero entry in each row, if it is a non-zero row, has to be 1, and the column where it occurs is special in the sense that there is no other non-zero entry in that very column, and then if you move on to the next row, if that also happens to be a non-zero row, then the first non-zero entry of that row should be placed on a column which is strictly on the right hand side of the column that we obtained for the previous row. Now, the sum total of these 3 requirements is what is known as the echelon form. If you actually look at the picture, then you will understand it is somewhat like an upper triangular form where the lower half is filled with zeros and the first non-zero entries appearing in the non-zero rows are 1, and then those columns where the ones are placed, they are the only non-zero entries in those columns, and then on the right hand sides of these ones you have possibly non-zero entries. So, this is what is called the row reduced echelon form of a matrix. Let us see some simple examples. We have seen the definition of row reduced echelon form of a matrix, and why we call it the row reduced echelon form is because that form can be achieved by successively applying elementary row operations on the matrix. Now, the question is there a precise method by which we can apply these elementary row operations and finally see the row reduced echelon form? And the second question is, what is that we are going to do with this row reduced echelon form? Now, the answer to the first question that I raised, that is about the precise method, is what is called the method of, or the algorithm of Gaussian elimination. And the answer to the second statement or the second comment would be, this will give us the precise method for solving a system of linear equations. In the subsequent slides, you will see that if we start with a system of equations given by Ax equal to b in the matrix notation, then we can apply the Gaussian elimination on the augmented matrix, and then we will reduce it to the row reduced echelon form, thereby reducing the system of equations, and finally this will give us solution for the system of equations that we started with. So, let us look at a couple of examples. The matrix A has 2 rows. Look at the first row. The first non-zero entry is 1, which is at the 1 1 position of the matrix, that is, it is on the first column of the matrix, and the other entry in the first column is 0. So, there is only one non-zero entry in that very column. And then in the second row, the first non-zero entry is again 1, which is in the 2 2 position of the matrix. So, that is, it is in the second column of the matrix, and the other entry in the second column is 0. So, it really fulfills all the requirements for echelon form. So, this is one good example of a matrix in row reduced echelon form. Now, proceed to the next example. B, the matrix, is not in row reduced echelon form. Why? Because if you look at the first row, the first non-zero entry is 1, but the column which contains this first non-zero entry, that is the first column, there we can see that there is one more 1 sitting at 3, 1 position, which should not happen. Similarly, if you look at the second row, then the first non-zero entry of the second row is indeed 1, but again, as per our requirement, the column which contains this 1 has also one more non-zero entry coming from the 1 2th position of the matrix. So, this is an example of a matrix which is not in row reduced echelon form. Now, Let me give you a kind of idea why we look for a row reduced echelon form. This was the definition of row reduced echelon form, and if you remember, I mentioned that echelon form means it's wedge shaped and something like upper triangular where the lower half is filled with zeros. So, if you recall the matrix notation of system of linear equations, which was written as Ax equal to B, where A was the coefficient matrix, X was the matrix of indeterminates x1, x2, xn, and if you follow the matrix multiplication closely, then you will see that if we achieve the echelon form for the matrix A or for the augmented matrix A stroke B, then what we achieve by doing this is that we are eliminating variables from this system. That means we are making the system of equations simpler by reducing it to a form where there are fewer numbers of unknowns to work with. So, this is indeed desirable in the sense that then you can understand that working back would be easier. So, the lower equations would have in a sense fewer number of variables. We first solve them and then we substitute them back in the upper equations, and eventually we come to a solution of the system of equations. It will become clear when we actually mention this particular method or the procedure for computing the echelon form. In fact, this is what is called the Gaussian elimination. This is the theorem which is going to describe the Gaussian elimination. So, the theorem says Gaussian elimination transforms any matrix into its row reduced echelon form. So, we will discuss about Gaussian elimination in the proof itself. The method consists of forward pass and backward pass in the following order. So, I am going to describe this forward pass and backward pass in a moment. Just recall that what we are trying to do is that we have a matrix, we will be applying elementary row operations on the matrix, and then eventually the form that we want is the echelon form. That means all the 0 rows will be placed at the bottom, the non-zero rows on top of the 0 rows. The first non-zero entry in each non-zero row has to be 1, and the column where that first non-zero entry sits has no other non-zero entry except that one. That is echelon form. Let us see what we mean by forward pass. This is the method by which we row reduce the matrix to a form where the first non-zero entry of each row is 1, and it occurs in a column which is strictly to the right of the first non-zero entry of each preceding row. What does that mean? That means if, let us say, the first row and also the second row are non-zero rows, and if the first non-zero entry of the first row is placed in the fourth column of the matrix, then the first non-zero entry of the second row should be placed on fifth column or afterwards. So, that is precisely what we mean by it occurs in a column which is strictly to the right of the first non-zero entry of each preceding row. Now, this is achieved by this forward pass. After this form is achieved, we now do the backward pass, which is the process of back substitution, in the sense that the row reduced matrix obtained after forward pass is further row reduced, so that first non-zero entry of each row is the only non-zero entry in its column, and this yields the final echelon form. What is that supposed to mean? After forward pass, we only achieved this much, that thus the first non-zero entry was 1 and the first entry occurs on a column which is special in the sense that in the next row the first non-zero entry occurs on a column which is strictly to the right of the first non-zero entry of each preceding row, but through backward pass what we achieve is that we can make all other entries of that particular column 0, and then the final outcome is what is called the row reduced echelon form. And let me remind you, we have been calling it row reduced echelon form is because the only operation or action you are allowed to perform on the matrix is elementary row operation, nothing else. Look at the matrix A, which is a 3 cross 3 matrix, and you can see that it is not in echelon form, because the first non-zero entry of first row is 1 which is appearing in the second column, whereas the first non-zero entry of the second row is appearing in the first column, which is not allowed. We therefore have to apply a suitable elementary row operation, so that this is flipped, that is, if we can push the second row up to the first position and push the first row down to the second position, then it is somewhat better. Look at step 1, that is what we have done. We have interchanged row 1 and row 2. Now, the first non-zero entry of the second row is appearing in the second column, whereas the first non-zero entry of the first row is appearing in the first column, and this is absolutely all right, but still it is not in echelon form for various reasons. Look at the third row, the first non-zero entry is 2, which is appearing in the first column, which is again not allowed. So, we have to do some more elementary operations. Now, the first thing that we would like to achieve is that in the first column we would like to have every other entry 0 except the 1/1th entry of the matrix. How do we do that? Look at step 2. If we apply the elementary row operation of the third kind, that is, the third row that is being represented by R3 is being changed to R3 tilde. And how do we do that? R3 tilde is equal to minus 2 R1 plus R3. What do we really get? If you look at A1, the matrix A1, look at the first row, that is R1, which is 1 0 1, If you multiply it out by minus 2, then you get minus 2, 0, minus 2. And then if you add that with the third row of A1, that is 2 minus 1, 1, then what you get is exactly the third row of A2, that is 0, minus 1, minus 1. Nothing happens to the first row, only the third row changes. And what is the benefit? Benefit is that now the first column has only one non-zero entry, namely 1, and that too at the 1, 1th position. Now we look at the second row. The first non-zero entry of the second row is surely 1, and it is placed in the second column, but the second column has one more non-zero entry, namely minus 1. That is not allowed. So we have to get rid of that minus 1 from the 2th position of the matrix A2 to be precise. Look at step 3. How do we do that? So that means we have to change the third row. That can be done again by applying the elementary row operation of third kind. So R3 tilde is the new third row, which can be achieved by adding R2 and R3. R2 and R3 are the second and third rows respectively of the matrix A2, and that yields the matrix A3, which is 1 0 1 0 1 2, and the new third row becomes 0 0 1. Now it is of course the one which we are looking for, that is the second column has now only one non-zero entry at the 2th position, and the entry is 1. And now if you look at the third row of A3, then the first non-zero entry, which is 1, and it appears in the third column, which is definitely the rightmost one you can have. But still we are not done yet, in the sense that the first non-zero entry of the third row is 1. That is perfectly all right, but it is placed on the third column, but there are other non-zero entries on the third column. So now is the time that we apply the backward substitution or the backward pass of Gaussian elimination. At the end of step 3, we are at the end of forward pass, because this was precisely the form that we were looking for, that the first non-zero entry of each non-zero row should be 1, and their position should be such that 1 is strictly on the right hand side as you move along the rows downward, but backward pass will give you the final form, that is, we do not want any other non-zero entries in these columns where the first non-zero entry of a row sits. Look at step 4. R2 tilde is equal to minus R3 plus R2. And then step 5, R1 tilde is equal to minus R3 plus R1. So this brings us to the final echelon form of the matrix after subsequent elementary row operations. Let us now see the effect of Gaussian elimination on a system of equations. So the theorem says that let Ax equal to B be a system of m linear equations in n unknowns. Let P be an invertible m cross m matrix, then PA alpha is equal to PB if and only if A alpha is equal to B. Okay. Now, recall that A is an m cross n matrix, because A x equal to B is a system of m linear equations in n unknowns, and we are taking a left multiplication of A by P. So, P has to have m columns. So, that is why we take P to be an invertible m cross n matrix. And what is alpha? Alpha is a solution of the system of equations A x equal to B. So, that means alpha has to be an n tuple. Let us see the proof. Alpha is a solution, therefore, A alpha is equal to B, and if we apply P, then P A alpha is P B, and it is a basic rule of matrix multiplication that you can shift the braces, that P A alpha is P B, and again if you apply P inverse, then you get P inverse P A alpha is P inverse P B. That is because P is invertible, and P inverse P is identity matrix, and therefore, A alpha is equal to B. Let us prove this statement. If A alpha is B, that is, if alpha is a solution of the system of equations A x equal to B, then P A alpha is P B if we multiply by P on the left hand side, and therefore, by adjusting the braces we can see that P A alpha is P B, and conversely if P A alpha is P B, then if we apply P inverse, then P inverse P A alpha is P inverse P B, and we can do that because P inverse exists, and since P inverse P is the identity matrix, we do get A alpha equal to B. Now, look at the corollary. Let A x equal to B be a system of m linear equations in n unknowns. If A tilde B tilde is the row reduced echelon form of A B, then A tilde x equal to B tilde and A x equal to B have the same set of solutions. So, we start with a system of linear equations A x equal to B. We look at the augmented matrix A stroke B. We row reduce it to the echelon form and we call it A tilde stroke B tilde. Therefore, we have a new system of equations A tilde x equal to B tilde. But the interesting fact is that this elementary row operations do not change the set of solutions for the systems of equations. And why is that so? Well, for the simple reason is that we have already seen that an elementary row operation amounts to multiplication by an elementary matrix of the right kind from the left hand side. And we also know that each elementary matrix is invertible, and inverse of an elementary matrix is also an elementary matrix of the same kind. So, that means if we have finitely many elementary row operations on A stroke B to row reduce it to A tilde stroke B tilde, then we are actually multiplying by an invertible matrix P, and that P is nothing but a finite product of elementary matrices giving rise to A tilde stroke B tilde. And we have already seen in the previous theorem that if alpha is a solution of the original system, then alpha is also solution of the changed system after multiplying it by p. Therefore, the corollary is proved. So, now we see that Gaussian elimination is indeed an effective method for solving a system of linear equations, in the sense that we first start with the system, look at the augmented matrix of the system, namely A stroke B. Now, we apply the Gaussian elimination to reduce it to row reduced echelon form, and then we solve the reduced system, and this solves the original system as well, because the set of solutions remain unchanged. And why we are calling it elimination is precisely what I mentioned some time back, was that by reducing it to the row reduced echelon form, we are actually getting rid of some of the variables in a sense. So, we are eliminating variables, and we are reducing the equation in the sense that we are probably getting fewer equations in fewer variables. Let us look at an example. So, here you see a system of 3 equations in 3 unknowns. The unknowns are x1, x2, x3. So, the corresponding augmented matrix is a 3 cross 4 matrix. You can see that it is a non-homogeneous system, because the B, which is 1, 6, 9, is a non-zero matrix, non-zero column matrix. Now, we are going to apply the Gaussian elimination to solve this system of equations. So, that means we will start with this augmented matrix and row reduce it to its row reduced echelon form. So, again a combination of forward pass and backward pass. You can see that first we are looking at the first non-zero entry of the first row, which happens to be 1, but sitting in the first column where there are other non-zero entries, and the second row, the first non-zero entry is 2, which is also sitting in the first column, which is not allowed. So, that means we have to push it to one of the second or third or fourth columns. So, how we do that is the following, that we are first making all the entries of the first column other than the 1th entry 0. That is what we have done after the second step. And then in the third step, you can see that we are looking at the second column of the matrix, where there are other non-zero entries, and after fourth step we have cleared it out. You can see that the second column has only 1 at the 2th position, and all other entries are 0. And you can see that the last row in the reduced form is the 0 row. So, there are only 2 non-zero rows in the row reduced echelon form, and it is indeed the row reduced echelon form. So, this is interesting in the sense that the reduced system of equations is now this, which is definitely reduced in the sense that there are only 2 equations instead of 3, and if you look at the second equation, there are only 2 variables involved. Now, how do we solve this? We can write x2 is equal to 4 minus 3x3. Now, substitute it back in the first equation, we get x1 is equal to 9 minus 5x3. Therefore, the set of solutions is the collection of all 3 tuples, such that first entry is 9 minus 5x3, second entry is 4 minus 3x3, and the third entry is x3, and x3 is varying freely in the set of real numbers. And if we rewrite it, we can rewrite it as the tuple 940 plus the tuple minus 5 minus 3 comma 1 t, and again t is varying over the set of real numbers. So, that shows that we have infinitely many solutions. And again, this is an illustration of a theorem which we discussed before, that any such solution is given by a particular solution plus solutions of the system of homogeneous equation. And 940 is indeed a particular solution, and this all these tuples given by -5, -3, 1 multiplied by t, they are indeed the solutions of the corresponding homogeneous system of equations arising out of this system. We now raise two very important questions which we propose, and this will be discussed in detail later. Question is that whether row reduced echelon form of a matrix is unique or not. Well, the Gaussian elimination indeed suggests so, but still we have to prove this fact. And the second one is that the number of non-zero rows in the row reduced echelon form, if we assume that the row reduced echelon form is indeed unique, then the number of non-zero rows in the row reduced echelon form, is that somewhat special? Well, that will be precisely the rank of the matrix. So, these are two things that we will prove after we introduce some concepts. This brings us to the end of chapter 1, that is the chapter on systems of linear equations. We have so far learned some important concepts like elementary row operations on a matrix, elementary matrices, row reduced echelon form, the Gaussian elimination, etc. Now, our aim would be to see it from a more general perspective. We will introduce the concept of vector spaces in the next chapter, and then we will revisit the systems of linear equations on a more general context.